Okay, there's three theorems that in my mind often go together because they have very similar names. One of them we already did, and that's the extreme value theorem. And I'll repeat that for you in a minute. Okay, but here's the three theorems that I always think of in a group. There's the extreme value theorem, the intermediate value theorem, and the mean value theorem. Okay, I'll remind you of the extreme value theorem. These all have to do with continuous functions. The extreme value theorem says if f is continuous, oh, that's not how you spell it. And has a closed interval for a domain, and that doesn't necessarily mean that the normal domain of f is just a closed interval. This might be something like a polynomial where the domain would be all real numbers, but where you're told to only look, say, from 1 to 5. Okay? All right, so if that's true, if you have a closed interval and you have a function that is continuous on that closed interval, then f will have an absolute max and an absolute min on that domain. Okay, so let's go ahead and draw a picture here. So let's say we're given a domain from A to B, okay, and f is continuous on that domain, and it's a closed interval from A to B, so the endpoints of my graph are going to be included. Okay, then you are guaranteed that there will be an absolute max and an absolute min for that graph. Okay, I'll just remind you here, look, that if the interval was open, then the endpoints do not be part of the graph. Then there might not be an absolute max and or min. This particular picture I drew does have an absolute min right around here, but there's no absolute maximum, because no matter how high you get, you can still go a little bit higher. Okay? But if the interval from A to B is a closed interval, and that's the domain you're given, you're guaranteed an absolute maximum and an absolute minimum. So that's the extreme value theorem. Now, let's look at what we call the intermediate value theorem. Okay, and here's what this says. Starts out the same way. If f is continuous on a closed interval, I'm actually going to write that. In fact, maybe up there where I wrote the extreme value theorem, maybe I should actually write the same way. If f is continuous on a closed interval from A to B, I'm just going to clean this up here. Then it will have an absolute max and an absolute min on that closed interval. Okay, now if you look at the function outside of that closed interval, then there might be a different max or min. For instance, maybe f will continue to do this Okay, so now there would be a different absolute minimum, right? So when I say if f is continuous on the closed interval from a to b, then f will have an absolute max and absolute min on the closed interval from a to b. I don't mean that the absolute max and min of the whole function is necessarily somewhere between a and b. I'm saying that if you only look at the part between a and b, then that part will have its own absolute max and absolute min. Okay? All right, let's get back to the intermediate value theorem here. If f is continuous on the closed interval from a to b, and f of a does not equal f of b, then for every value, let's call it y, between f of a and f of b, there is some c between a and b such that f of c equals y. Okay, what is that saying? So again, let's say here's a and here's b, and let's say that f of a does not equal f of b. So maybe f of a is down here and f of b is up here. That means our graph would start at that point and stop at this one. Okay. I'll draw a continuous graph in between there in a minute, but let's not yet. Let's right now just put the two endpoints. Okay, it says for every value y between f of a and f of b. So let me just pick a place between these two and call it y. Okay, it says there has to be some number in this range where f of that number will equal y. So let me show you what that means. I'm going to just draw a line across here. Whoops. What they're saying is this. If I want to get from that first blue point to the second blue point with a continuous function, I must cross that red line at least one point. And wherever it is that I cross that red line, there's my c. The theorem is telling us that there has to be some point between a and b where the graph will cross the red line if the function's continuous. It might even happen more than once. Could go like this, in which case it crosses 3 times. So there's 3 different values that could be called c. Okay? If the graph was not continuous, then there might not be such a c, because you might have for instance, a jump discontinuity. And then there is no place where the graph crosses the red line. So there is no number here that I could plug into the function to get this as the output. But if the function is continuous, then I must cross the red line somewhere between A and B. That's what the intermediate value theorem says. We're not going to prove it. It's beyond the level of this class for the most part. Okay, but let me show you something that this could be useful for. This can be really useful for estimating roots. Like, for instance, suppose you forgot exactly how big is, let's say, the square root of 2. Okay? We can use the intermediate value theorem to figure that out. Let me show you. Using the intermediate value theorem, to estimate the square root of 2. Okay, so what you can do is you can say, all right, I want to figure out how big is the square root of 2. So in other words, let's write x equals the square root of 2. And we'll try to figure out approximately, we won't get it exactly, but just an estimation for x. Okay, so what I'm going to do is subtract the square root of 2 from both sides and write x minus the square root of 2 equals 0. Okay, so let's write f of x equals x minus the square root of 2, and we want to know when does that equal 0. Okay, so here's what you can say. This is actually pretty trivial. Once I say this, you're going to say, oh yeah, I mean, we could have thought of that. And all I'm doing is just pointing it out. Okay, so here's what you can do. You can find a number where f of x will be positive. Okay? So for instance, what I mean is this. Do you agree that the square root of 2 is somewhere between 1 and 2? You probably agree with that, right? Because the reason why is the square root of, because 1 is the square root of 1, so the square root of 2 is bigger than that, and 2 is the square root of 4, so the square root of 2 is less than that. So I think we can agree that the square root of 2 is somewhere between 1 and 2. So what you can do is you can say, all right, so let's say here's 1 and here's 2. Okay? The square root of 2 is somewhere between there. In other words, if I plug in 1, I will get f of 1 equals, let's just do some scratch work here. F of 1 equals 1 minus the square root of 2. And I'm sure that that's a negative number, because I know the square root of 2 is bigger than 1. Okay? Let's not worry about what is it exactly. Let's just say that I know it's negative. I'll just put a dot there. And what about f of 2? That's 2 minus the square root of 2. I know that must be positive, because 2 is the square root of 4. So the square root of 2 is smaller than 2. So when I subtract the square root of 2 from 2, I know I'm going to get a positive answer. Okay? And I know that this is a continuous function because it's a polynomial. So that means that this graph has to cross the x-axis, somewhere between 1 and 2. Okay? And then here's what you do. This is called bisecting. What you can do is just cut that in half. Take the number 1.5, which is 3 halves, right? Maybe let me write 3 halves instead. So let's figure out which is bigger, 3 halves or the square root of 2. Which one's bigger? Does it go like that or does it go like that? Well, that's easy to do. Square 3 halves and you would get 9/4. Square the square root of 2 and you get 2. What's bigger, 9/4 or 2? 9/4 is bigger, which means that 3 halves is bigger than the square root of 2. So, whoops, I didn't mean to do that. So, f of 3 halves equals a big number minus a smaller number, which will be positive. So we'll put a dot here. So the intermediate value theorem tells us that the graph of f has to cross the x-axis somewhere between 1 and 3 halves. So now you can say the square root of 2 is somewhere between 1 and 1.5. Okay? Then you cut that in half. You get 5 halves. And you do the same thing. Which is bigger, 5 halves or 2? Well, when I square them, I get 25. Whoops, I said 5 halves. And of course, I meant 5/4. Okay, so what's bigger, 5/4 or 2? Well, when you square 5/4, you get 25/16, which is smaller than 2. So 5/4 is smaller than the square root of 2. So f of 5/4 is a number minus a bigger number. So that will be negative. So now I can say that the graph of f crosses the x-axis somewhere between 5/4 and 3 halves. So the square root of 2 is somewhere between 1.25 and 1.5. And then you just keep halving over and over again until you get whatever level of accuracy you would like. Okay? All right. What's the third one? So we have the extreme value theorem, the intermediate value theorem. The third one that I grouped together is called the mean value theorem. Okay, the mean value theorem says this. If f is continuous on a closed interval from a to b and differentiable on the open interval from a to b. So that means you have a continuous function from a to b, and this function has a derivative at every number between a and b. Okay, then there exists some value c between a and b such that f prime of c equals f of b minus f of a over b minus a. Okay, let's look at a picture of that. This is what it's saying. Let's say we have here a, and we have here b, and let's just say that f does something like maybe this. Okay. Do you recognize what number this is? Think about that for a minute while I write this. That point is a f of a, and this point is b f of b. What does this number tell you? Isn't that the slope of the line connecting those 2 points? It is, right? Whoops, I didn't mean to erase that. I meant to draw a red line. That number there is the slope of the line segment connecting the 2 endpoints, right? Now what the mean value theorem says, it says that somewhere between a and b there is a point where the derivative will equal that number. What's the derivative tell you? It tells you the slope of the tangent line, right? So in other words, the mean value theorem is saying somewhere between a and b there has to be a point where the tangent line will be parallel to that red line that I drew. And I can see that there's probably 2 places where that happens. Okay, look for instance here. It looks like the tangent line there is parallel to the line segment I drew, which means the derivative at c will be the same as the slope of this line, which is this number right here. Okay? Looks like there's probably another place that happens somewhere over here as well. So there's probably a couple places it happens. The mean value theorem says that you're guaranteed that it's going to happen in at least one place. Okay? And by the way, this f prime of c, you already know that is the instantaneous rate of change of f at x equals c. This number, by the way, is the average rate of change of f from x equals a to x equals b. So the mean value theorem is saying that the instantaneous rate of change at some point will equal the average rate of change across the interval. Okay? I would like to go ahead and prove this one with you just so you can see how such a proof would be done. The trick to proving this is to actually do another theorem first, and then that makes this proof super easy. So let me introduce you to something called Rolle's theorem. This was proven first in the course of history. Okay, it says if f is continuous on the closed interval from a to b, and f of a equals f of b, then there is some c between a and b such that f prime of c equals 0. Okay, let's prove that. That's easy to prove. Okay, so if f is constant on the interval from a to b, I misspelled that, hang on. Then f prime of x equals 0 for all x between a and b. So if you're trying to find a value c where f prime of c equals 0, then you could pick any c between a and b. Okay, so that's one possibility, is that f is constant, and in that case Rolle's theorem is easily true. Okay, now if f is not constant, that's the other possibility. If f is not constant on the closed interval from a to b, then the absolute max and absolute min, which are guaranteed, how do you spell that? Is it that way? I'm not sure. I'm just going to leave it like that. Forgive me if it's wrong. Okay, which are guaranteed by the extreme value theorem. The extreme value theorem tells us that f will have an absolute max and an absolute min on the closed interval from a to b. And if f is not constant, then that absolute max and absolute min cannot both be at the endpoints. Because, for instance, if f of a was the absolute maximum and f of b is the absolute minimum, and f of a equals f of b, then the absolute maximum and the absolute minimum would be the same, which would mean that the function is continuous, constant. But we're looking at the case where f is not constant. And so the max and min can't be the same. So they can't both be at the endpoints because the endpoints are the same. Okay? So either the absolute max or the absolute min, or both, one or the other or both, have to occur somewhere between A and B. Okay? So there must be some C between A and B where f of C is the absolute max or the absolute min. Thus, f prime of C would equal 0 because it's a maximum or a minimum and it's not at the endpoint. Remember, maximums and minimums can only occur in three places: the endpoints, the places where the derivative doesn't exist, and the places where the derivative is 0. Well, C is not at the endpoints, and f prime of C exists. Oh, I forgot to write that in there, though. Excuse me, let me add that in. I left that out. If f is continuous on the closed interval for A to B and differentiable on the open interval from A to B, and f of A equals f of B. That's what I should have said. So C is not at the endpoints. F prime of C exists because f is differentiable. So therefore, the only way C can have a f of C could be the max or the min is if the derivative is 0. Okay, so just pause the video and look at that for a minute. That's Rolle's theorem. Now, proving the mean value theorem now becomes super easy. And even though this might be looking a little bit out of order, what we're going to do is I'm going to scroll up and we will write the proof of the mean value theorem right here. Okay. So what you do is you define G by G of x equals f of x minus this number, f of b minus f of a over b minus a times x. Because f is continuous on the closed interval from A to B, then G is continuous on the closed interval from A to B. That looks like a 9. Let me fix that. A. Okay, and because f is differentiable on the open interval from A to B, then G is differentiable on the open interval from A to B. Which means, by Rolle's theorem, there is some C. Sorry. Let me point out one more thing before we say that. Before we mention Rolle's theorem, I need to point out one more thing. Darn it. Okay, which is let me just give myself some space here. Okay, so I need to show that G of A equals G of B. So let's write G of A. What would that equal? That'll equal f of A minus f of b minus f of a over b minus a times a. And what will g of b equal? G of b will equal f of b minus f of b minus f of a over b minus a times b. Now those are actually the same. It's not obvious, but look. Let's write down g of b minus g of a. So that would equal, let's see if we can fit it in here, f of b minus f of b minus f of a over b minus a times b, and then it'll be minus g of a, so that would be minus f of a plus f of b minus f of a over b minus a times a. Okay, we can just do a little bit of organization here, and that'll be f of b, that takes care of this one, minus f of a, that should be an a, that takes care of this, and then we're going to do plus f of b minus f of a over b minus a times a, that's this, and then minus f of b minus f of a over b minus a times b. That's this. So now I got all four parts. We can do some combining, and we'll get f of b minus f of a plus, now watch this, f of b minus f of a over b minus a times a minus b, right? Times a minus b. Okay? Which is the same thing as writing f of b minus f of a minus f of b minus f of a over b minus a times b minus a. And these cancel. And so we're left with f of b minus f of a minus f of b minus f of a, which is 0. So g of b minus g of a equals 0. Which means g of a equals g of b. So g is continuous on the closed interval from a to b. G is differentiable on the open interval from a to b. And g of a equals g of b. So we can use Rolle's theorem on the function g. By Rolle's theorem, there is some c between a and b such that g prime of c equals 0. But what's g prime of c? Well, here's g right there. G of x equals that. So what's the derivative of g of x? G prime of x would equal f prime minus f of b minus f of a over b minus a, right? G prime of x would equal f prime of x minus this number. So G prime of c equals f prime of c minus this number. And we said G prime of c equals 0. So f prime of c minus this number equals 0. So f prime of c has to equal that number. And that proves the intermediate, I always get them mixed up when I'm speaking. That proves the mean value theorem. Okay, that's all for today.